In this chapter, we will go over the types of bonds that make molecules. We will talk about the nomenclature of inorganic compounds and how to draw their shape and figure out their geometry. First, let's go over the periodic table. This is a revision for chapter 3. So we said that the periodic table is divided into two parts, you guys. Metals and nonmetals. And the metals, they do constitute a huge chunk of the periodic table. It is the simply group number 1, which is the alkali metals. A group number 2, which is the alkali earth metals, and there these are considered to be metals. And then you do have the D block in there, which is the transition metals. So this is the D block, and these are the transition metals. The transition metals are end in the d orbital, and they are less metallic than groups 1 and 2. Okay, and then you do have the nonmetals. The nonmetals are in the green color. Between the metals and the nonmetals, you do have what we call the metalloids. Metalloids are poor metals, and these are, let's highlight them, these are boron. We have silicon in there, and then germanium and arsenic, and then antimony and tellurium and astatine. So what are these? These have a properties between metals and nonmetals. So they are neither metals nor nonmetals. Elements that are before those are considered to be metals. Elements after those are considered to be nonmetals. And then, as I said, we have the noble gases there. The F block is considered to be metals as well. So, in order for these elements to make bonds with another elements, we need to know the valence electrons for the atoms that constitute these elements. Remember last time when we said that every element is made up of 6.023 times 10 to the 23 atom, right? So now when we consider the valence electrons, we're considering the valence electrons for one atom. See how tiny and small that is. So I'm going to refer as the the element as an atom now, and we want to know the valence electrons of the hydrogen atom. And again, the hydrogen element is made up of 6.023 times 10 to the 23 atoms. So it's important to know the valence electrons. Why do we want to know the valence electrons? Because the valence electrons tell me how many electrons are there in the outermost shell of the atom. So for example, if I am talking about, let's say, lithium, lithium has an atomic number of 3. If you draw the electronic configuration of lithium, you know that lithium ends in 2, and this is the S block, and it's 1. So it's going to be 2s1 in there, right? So that you have a total of 3 electrons total, because this is what lithium is. Lithium has 3 electrons in there. So if I want to know how many electrons are there in the outermost shell of lithium, so this is the nucleus of lithium, and around the nucleus you do have the n equal to 1. The n equal to 1 has 2 electrons, so I'm just going to draw the 2 electrons in there. Okay, you can draw them anywhere you want, just going to draw them like this. And then the n equal to 2 has 1 electron in there. Now there is no shell after the n equal to 2 that is filled. So the outermost shell for the lithium, which is the last shell farther away from the nucleus, is n equal to 2. And this shell over here is very important because the electrons on the shell, these are responsible for the lithium making bonds with another atom. So this is why we care about the valence electrons. So now I would say, okay, the valence electron for the lithium, it's in the outermost shell and it is equal to 1. So the K shell is completely filled. So this is the K shell in there. It is completely filled. And then the L shell is the one that is not filled. This is N equal to 2. This is equal to 1. So I say that lithium has valence electrons is equal to 1 in there. Okay? That is for The lithium. So when I wanted to go ahead and represent the valence electrons of the lithium, then I would say, okay, I'm going to represent the valence electrons as a dot. And I would say lithium has one electron like that. So the valence electrons, if you notice, this is equal to the group number. So lithium is in a group number 1, so it has one electron in its outermost shell. Let's consider, for example, magnesium in there. So magnesium has an atomic number of 12. So if we want to draw the electronic configuration, this is 1s2, 2s2, 2p6, and it's supposed to end in 3s2. This is a 3s2 in there. Okay, then the n equal to 1 is completely filled. N equal to 2 is completely filled. This is the K and this is the L. And then I have N equal to 3. So the outermost shell for the magnesium, I'm looking at the nucleus of the magnesium and then the shells around that nucleus. This is N equal to 1, this is N equal to 2, this is N equal to 3. So the electrons in N equal to 3 are 2 electrons in there, okay? Compared to 8 electrons in N equal to 2. So we can draw the 8 electrons. It's basically, remember what I said last time, just to be on the same page, that electrons, they do not orbit around the nucleus in a circular motion. It's rather than elliptical motion, but I am drawing the shells as circular because it's easy for me to represent. But please pay attention to this note. So you do have three, this is 4, 5, 6. We can continue like that, 7 and 8. Okay. We can close that. So I'm drawing them as circular, but they are actually elliptical. And they're in N equal to 1 has 2 electrons in there. Again, what we care about are the electrons in the outermost shell. And these are two. These are the ones that are involved in bonding with other atoms. So now when I want to go represent magnesium, magnesium is in the group number 2, so it does have two valence electrons. It doesn't matter where I draw them around the magnesium. I can draw them anywhere, but it just have two valence electrons because it is in a group number 2. So what are valence electrons? These are the group number. These are electrons that are present in the outermost shell. So let's have more examples over here. Hydrogen is in a group 1. So you can draw the electronic configuration and figure it out, but it's easy to just relate it to the group number. Magnesium, as we mentioned, this is group number 2. Boron. Boron is in a group number 3. So boron has 3 valence electrons. This is 1, 2, and 3. Carbon, it's in a group number 4. So it has 4 valence electrons, and normally I draw them like this. I don't pair an electron except whenever all of the sides have electrons, then I start pairing. Let me show you. For example, nitrogen. Nitrogen is in a group number 5. So I do 1, 2, 3, and 4. Now I have completed all the 4 sides of the nitrogen. Then I go ahead and do 5 over there, and this is considered to be pairing. So this is considered to be pairing of electrons. Fluorine is in a group number 7. So I do 1, 2, 3, 4, and then I pair 5, 6, and 7. Okay? You can pair in any way you want. It's not a big deal. Neon is octet. Neon has 8 electrons. So this is going to be 8 electrons like that. Oxygen is in a group number 6, so it is 1, 2, 3, and 4. This is 5, and this is 6. I can pair these electrons. I can pair this side over here. It doesn't matter. It doesn't have to be those two sides. Okay. Lithium is in a group number 1, so it has 1 electron. Now, all of these atoms, they can gain and lose electrons. And when they do, we're going to call them ions. Okay? The positive ions, we call those cations. So positive ions, we call them cations. And the negative ions, we call them anions. And we use the term ions in general to describe both positive and negative ions. So by definition, metals, they lose electrons. So far you know where the metals are. So metals, they lose electrons. And in chemistry, we represent losing by a plus sign. Non-metals, they gain electrons. And in chemistry, we represent gaining by a negative sign. Okay? So let's go ahead and put the charges of the atoms in there when they become ions for different groups. So for the group number one, these are metals with the exception of hydrogen. Hydrogen is not a metal. Hydrogen is a non-metal. So pay attention to that. But it still behaves like the rest of the group number one. Hydrogen can lose one electron because it is in the group number one. So the amount of the electrons that the metal loses corresponds to the group number, with the exception of the transition metals. The transition metals have no rule, but since they are metals, they're going to lose electrons. There is a table specifically for transition metals. I did skip the transition metals in here and stuck only to groups number one, number two, three, four, five, six, seven, and then eight. Okay? So again, transition metals, these they just lose electrons, and these are exceptions. They do have a table on their own. I'll show it to you at the end. I'll share it with you. And the transition metals, they can lose different number of electrons depending on whatever they are bonded with. So group number one loses one electron. And when they lose one electron, they become a plus charge, plus one charge. Group number two, they lose two electrons and they become a plus two charge. So you write it like this. You write, for example, the beryllium in there. You write it as a 2 plus, or you can write it as a beryllium plus 2, whatever you want, okay? Although it is more correct to write it as a 2 plus, but you can also write it as a plus 2. No problem with that. Group number 3, they can lose 3 electrons in there. So group number 4 now. Group number 4 is always an exception. We know that carbon is a nonmetal, right? And silicon, if you look at the periodic table in there, so carbon, silicon. Silicon is a poor metal, which is a metalloid. Silicon is a metalloid. So group number 4 is this group over here. Group number 4 is an exception because group number 4 can either gain or lose. Group number 4 can either gain 4 electrons or lose 4 electrons there. So it can have either a positive 4 or a negative 4 charge. So here it can have either a plus 4 or a negative 4 charge. Then group number 5. Group number 5, since it is group number 5, it has 5 valence electrons. So have 5 valence electrons in there. Always, whenever you are gaining electrons for non-metals that are gaining electrons, they always gain to their maximum capacity, and their maximum capacity is 8 electrons. So if a group 5 has 5 electrons, it needs to gain 3 electrons to become 8 electrons, to become octet. So this means that it forms a simple ion charge of negative 3. So if you look at group number 5, it's a charge of 3 negative. Why? Because they are a group number 5 and they need the 3 electrons to become 8 is going to gain. Group number 6. The group number 6 has 6 valence electrons, right? So they need 2 more to become 8, to become octets. So this is why their charge is 2 negative. They gain 2 electrons. Group number 7, they need 1 electron to be 8 electrons. So they gain just 1 electron in there. Now, group number 8, they neither gain nor lose. They have already 8 electrons. They are already octet. So their charge is going to be 0. Guys, just to refresh your memory about the representative elements. Representative elements, these are elements that belong to the periodic table other than the transition elements and the noble gases. We call those representative elements. So they are a combination between metals and nonmetals, excluding the transition elements and the noble gases. So we talk about in general, you guys, when we talk about a representative metal, these they do form ions, and the ions they form have the same positive charge as the number of the group that they belong to. So you look at the metal in there and you see, okay, calcium is in the group number 2, so it is a plus 2 charge. If I'm talking about representative nonmetals, they do form ions, and we said that they gain electrons. So when they gain electrons, their charge is going to be a simple negative charge. Okay, so their charge is going to be a negative charge. And in order to calculate the charge, normally what we do is it's always negative, you guys. Your answer is not going to be negative, but it's always going to be negative. So what you do is you take 8 and you subtract that from the number of the group that they belong to. So phosphorus belongs to group number 5. So this is going to be 8 minus 5. This is going to be 3. So I know that phosphorus is going to gain 3 electrons. So I'm going to put negative there and it's going to be 3. Okay? Because it's a non-metal. Oxygen, for example. Oxygen is in the group number 6. So I say, okay, that is 8 minus 6 because I need 8 electrons. I need oxygen to be 8 electrons. Right now, oxygen has 6 electrons. So how many electrons does it need to gain? It needs to gain 2 electrons in there. So I would say, okay, oxygen is going to gain 2 electrons in order to become octet, to become 8 electrons. Same thing for, let's say, chlorine, for example. Chlorine is in the group number 7, so chlorine needs just 1 electron in order to become 8 electrons. So when I want to represent the chlorine, I simply represent it by a negative charge. Okay, and all of those, when I represent those by negative charges in there, this means that they have 8 electrons. Okay, so phosphorus in there, if it's -3, then it should have 8 electrons. Oxygen, if it is -2, then it should have 8 electrons. Chlorine, it should have 8 electrons in there. And simply we throw the 8 electrons, and this is the ion. It's called the ion of the element.